Hello students, I am Trupti Patel from Arihant College of Arts, Commerce and Science. Today we are going to study Gibbs energy. American theoretician J.W. Gibbs introduced a new thermodynamic property called Gibbs energy, usually denoted by G. Gibbs energy is defined as G is equal to H minus Ts, where H is enthalpy, S is entropy of the system. Since H, that is enthalpy, T and S are state functions, G, Gibbs energy, is also state function. A change in Gibbs energy depends on initial and final states of the system and not on a path connecting the two states. The change in Gibbs energy at constant temperature and constant pressure is given by delta G is equal to delta H minus T delta S. Gibbs energy and spontaneity. The total entropy change that accompanies a process is given by delta S total is equal to delta S system plus delta S surrounding. The subscript SYS that refers to the system is dropped hereafter. SYS is for system and SURR is for surrounding. Relation between delta G and delta S total. According to second law of thermodynamics, for a process to be spontaneous, delta S total is greater than 0. If delta H is the enthalpy change accompanying a reaction, that is system, the enthalpy change of the surrounding is minus delta H, with delta S surrounding is equal to minus delta H upon T. Substituting this value in the earlier equation which we studied, so delta S total is equal to delta S minus delta H divided by T. Thus, delta S total is expressed in terms of the properties of the system only. Rearranging the terms, delta S total is equal to delta H minus T delta S. Substituting in equation, delta G is equal to minus T delta S total. For a spontaneous reaction, S total is greater than 0 and hence delta G is less than 0. At constant temperature and pressure, Gibbs energy of the system decreases in a spontaneous process. The second law leads to the conditions of spontaneity, which are summarized here. First, delta S total greater than 0 and delta G less than 0, the process is spontaneous. Second, delta S total less than 0 and delta G greater than 0. The process is non-spontaneous. Third, delta S total is equal to 0 and delta G is equal to 0. The process is at equilibrium. Spontaneity and delta H or delta S. From delta G is equal to delta H minus T delta S at constant temperature and pressure. The temperature term determines relative contribution of delta H and delta S to delta G. Delta H and delta S are both negative. Then delta G will be negative only when delta H is more negative than T delta S. This is possible at low temperatures only. Delta H and delta S both positive, delta G will be negative only if delta Ts greater than delta H. That is possible only at high temperatures. Third, for delta H negative and delta S is positive, it follows that delta G is negative regardless of temperature. For delta H positive and delta S negative, then delta G is positive regardless of temperature. Such reactions are non-spontaneous at all temperatures. Next we are going to study temperature equilibrium. For equilibrium, delta G is equal to delta H minus T delta S. Therefore, T is equal to delta H upon delta S. T is the temperature at which the change over from spontaneous to non-spontaneous behavior occurs. Delta H and delta S are assumed to be independent of temperature in above equation. Introducing of temperature dependence of delta H or delta S would not cause significant error for the moderate temperature range. Next, we are going to study Gibbs function and equilibrium constant. Gibbs energy change for a chemical reaction is given by delta G is equal to delta G degree plus RT ln Q, where delta G degree is standard Gibbs energy change, that is the Gibbs energy change when the reactants and products in a reaction are in their standard states. Q is called reaction quotient. Q is analogues to that of the equilibrium constant and involves non-equilibrium concentrations or partial pressures in case of gaseous reaction. Consider, you can see the reaction A plus B gives you C plus D. You can see the difference, capital A, capital B, capital C, capital D. So this is the reaction. So delta G is equal to delta G degree plus RT ln QC, which is equal to delta G degree plus RT ln C raised to the power small c multiplied with D raised to the power D divided by capital A raised to the power small a multiplied with capital B raised to the power small b, or delta G is equal to delta G degree plus RT ln QP, which is equal to delta G degree plus RT ln PC raised to the power small c multiplied with PD raised to the power small d divided by PA raised to the power small a multiplied with PB raised to the power small b. These are the two different ways to write delta G. Delta G is equal to delta G degree plus RT ln QC. This is the one form. Just we have studied how to elaborate that. And the another form is delta G is equal to delta G degree plus RT ln Qp. This is the second. Moving further, when the reaction reaches equilibrium, delta G degree is equal to 0 and Qc and Qp becomes Kc and Kp respectively. Thus, 0 is equal to delta G degree plus RT ln Kc and 0 is equal to delta G degree plus RT ln Kp, or in terms of delta G degree is equal to negative RT ln Kc and delta G degree is equal to negative RT ln Kp. When we remove ln, we go for log. So delta G degree is equal to negative 2.303 RT log to the base 10 Kc, and delta G degree is equal to negative 2.303 RT log to the base 10 Kp. Thank you.